All right, good afternoon, ladies and gentlemen, and welcome to our presentation on nanocrystalline cellulose-reinforced composites for speaker design. I'm Alexander. Here with me today is Kevin. Out on the floor manning our table are Tyler and Tim, our other group members, and we would like to extend an extra special thank you to our consultant, Dr. Boshin Zhao, for his guidance and assistance in this project. Now, first we're going to start off with, how does a speaker work? A speaker is composed of three main components: a permanent magnet, a voice coil, and a cone. Electricity is pushed through the voice coil, which creates electromagnetic forces of attraction and repulsion. These forces are controlled by the strength of the magnet, as well as how much current is pushed through the voice coil. These forces is what causes the cone to move. When the cone moves, it compresses air, and we interpret that as sound. Now, cones are made from a variety of materials: metals, such as aluminum, polymers, composites, paper, and paper composites where specialty fibers are interwoven in the cellulose matrix, such as Kevlar and carbon fiber. Each of these different materials have their advantages and disadvantages. For example, metals, such as aluminum, it's stiff and it's easy to machine. So you use it in an application such as in your cell phone where you have a small speaker, or in your earbud where you have a tight, small area to work with. The problem with this material, though, is that you could build up resonance on the speaker cone, and this resonance is what's responsible for that tinny sound associated with low-quality earbuds. Polymers might be better used in an application such as in your car. You step into a puddle, you have water on your feet, you step into your car and you splash the speaker. If it were paper, you could ruin the speaker, but if it's polymer, something that's resistant to water, you don't have that problem. Paper, however, is used in applications where speaker quality is the most important. It is stiff, but it doesn't build up resonance like metals do. And so that's where you see it in your home theater. However, the stiffness can be improved by making paper composites, and that's why they do that, reinforcing it with Kevlar and carbon fiber.
Now, we did something similar to this, although our composite uses novel nanomaterials instead. We looked at nanocrystalline cellulose, or NCC, and microcrystalline cellulose, MCC. The reason we're interested in these materials in particular is because they're cellulose-derived, so they're very compatible with the paper matrix. Additionally, they come at a relatively low cost, and they have a high strength. By implementing them into our cellulose matrix, we hope to increase the stiffness-to-weight ratio, which is also known as the specific modulus. But first, let's talk about NCC a little bit longer. Now, NCC is a very interesting material. As you can see here, the elastic modulus and tensile strength of NCC are actually higher than that of Kevlar and carbon fiber, which are currently used in speaker cone materials, and comes at a comparable cost. Now, the secret to NCC strength is that it has a very high aspect ratio, has a lot of surface area given its volume, and a lot of hydrogen bond density. So these are active sites that are able to bind and have strong cohesive forces, giving it a high strength. Now, granted, other nanomaterials do have an even higher strength, such as carbon nanotubes. However, these would not be as compatible with the cellulose matrix and come at a prohibitively high cost. Speaking of cost, though, you might be thinking, NCC, that sounds like a boutique chemical to me. But if you look at the cost breakdown of a typical driver, this cone is only about 0.5% of the total cost. By contrast, the magnet, which is generally made of the rare earth metal neodymium, costs about 70% of the cost. So by using NCC to create a cone that has a higher specific modulus, so it is stiffer even at a lower mass, you would be able to reduce the size of the magnet necessary to drive it. So even if you were to double the cost of the cone, the reduction in cost from the magnet reduction would have an overall effect of cost savings. And this brings us to our design rationale. What we have done is created stronger paper, that is to say, paper with a higher specific modulus. This allows for lighter cones in driver fabrication. Lighter cones can use a smaller magnet to drive them, and that leads to a lower cost for manufacturers, which can then be passed on to the consumer or kept in the pocket of manufacturers.
Now, the key to this design project is to produce a stronger paper, and the way we go about doing that is adding nanocrystalline and microcrystalline cellulose. As Kevin just explained, taking advantage of the increased surface area to weight ratio, we can form more hydrogen bonds between individual cellulose fibers. Cellulose in a paper matrix is held together, among other things, by the hydrogen bonds present between the fibers when they overlap. By incorporating the nanocrystalline cellulose, it acts somewhat like an adhesive, in a sense, creating more hydrogen bonds between the fibers, increasing the strength of the material. We add microcrystalline cellulose to help bridge the size gap between the large regular cellulose fibers, creating more connection points for increased strength. The particular formula we used consisted of 94% raw softwood pulp, 5% microcrystalline cellulose, and 1% nanocrystalline cellulose. The reason we chose this particular formula is we believe that this would be enough additives to exhibit some sort of impact on the mechanical strength of the composite, and at the same time, according to literature review, this amount of additive is enough so that we can use mathematical models to estimate the improved strength of the composite. Our calculations suggest that this composite should have a 12.6% increased specific modulus as compared to a formula entirely made of raw softwood pulp. Now, when we started this project, we set forward three main objectives that we wanted to achieve. First and foremost, we want to make a composite using the microcrystalline and nanocrystalline cellulose, and we wanted to demonstrate a 7.6% increase in specific modulus. Why did we choose 7.3 rather, not 7.6. Why did we choose 7.3% increase? According to our mathematical model as to how much a speaker costs in the breakdown, we figured that that would save speaker manufacturers 5% in terms of materials if we can improve the strength of the cone that much. Our secondary objective is to make sure that the nanocrystalline and microcrystalline cellulose can be easily added into the cellulose matrix. We don't want to complicate the manufacturing process. By complicating the process, adding new steps, we are inevitably going to increase the cost of the driver, and that's what we're trying to avoid. Our tertiary objective is to actually install the NCC-MCC composite into a working speaker driver and demonstrate that our composite driver exhibits an audio fidelity 10% or greater than that of a driver made entirely out of regular cellulose. We performed our measurements following TAPI standards. These are the industrial standards that are followed by industrial manufacturers for all of our evaluation.
Now, long before TAPI, the invention of paper happened. It's a very mature technology dating back almost 2,000 years. Back then, they used to take mulberry bark, dilute it, grind it up, and pound it into mats. Since then, the process has gotten a little bit more sophisticated, so we enlisted in the help of the BioSentinel Paper Research Network at the University of McMaster in Hamilton. There, we had access to their TAPI standard laboratory-grade equipment where we were able to take raw softwood pulp, soak, disintegrate, beat, and mix it to create a well-dispersed solution of cellulose fibers. Into this solution, we then added our NCC and our MCC. Once again, we redispersed it, created a homogeneous solution, and then we filtered it through a fine wire mesh. This creates a paper handsheet. This is then treated under high pressure and temperature to remove any remaining moisture. We created 32 handsheets of varying compositions, and from them we made 88 test strips for tensile testing. From tensile testing, we were able to get the Young's modulus of elasticity, which, when normalized for density, will give you the specific modulus. Here you can see that there are 4 different compositions we looked at for this study. The red bar is our standard pure cellulose paper. The green bar is our 1% NCC, 5% MCC composite that we've been discussing. In addition, we also looked at 6% only MCC and 6% only NCC to make sure no funny business was happening where one fiber was doing all of the work. As we expected, the greatest performance did in fact come from our hybrid composite with both NCC and MCC. Our mathematical prediction was an increase in specific modulus of 12.6%, and we were able to achieve, on average, an increase of 12.3%. This exceeded our primary objective of increasing the specific modulus by 7.3%.
Now, after the hand sheets were made, we had to install them into a driver to see how they would perform audiometrically. The way we went about doing this is first we purchased commercial drivers manufactured by McBride that were 4 inches in diameter, had a full range frequency performance, and had a paper cone. We carefully removed the paper cone, and using that paper cone as a stencil for on top of our composite, we created a new paper cone, which then was reinserted into the driver and sealed with liquid adhesive. On the bottom left, you can see an image of the driver before it was modified, and on the bottom right, you can see that same driver after the NCC-MCC composite was installed. Now, how do you go about evaluating how a speaker performs? One way is you can play your favorite music through it and judge that way, but that's not very scientific, nor is it very quantitative. The quantitative approach is to perform what's known as a frequency response analysis. The setup for this is quite simple. You take the driver and you place it in an enclosure, and you place that enclosure inside of an anechoic chamber. This is a room with padding on the walls that prevents any sort of reflection of sound and prevents sound coming into the room, and then you set a high fidelity microphone up in front of the driver. Now, the computer knows what it's telling the speaker to play. It tells the speaker to play a pseudo-random frequency sweep across the entire range of human hearing. The microphone evaluates what the speaker actually plays, and the comparison is what you see here. In this case, this is an ideal response. It is completely flat. This means that your microphone is picking up exactly what the computer told the speaker to play. Now, in reality, no speaker can achieve this. There's no speaker that is able to achieve a perfectly flat response. This is our data. So in this particular setup, we had our prototype placed 50 centimeters away from the high fidelity microphone. Red shows the performance of our composite, the black shows the performance of the standard, and that green line that you see up there at the top is the ideal perfect flat response that a perfect speaker would give. What you see is a great deal of overlap. This suggests that the NCC-MCC composite may be useful in audio applications. When we take a closer look at the data, that is when we place the microphone only 10 centimeters away from the speaker, what we find is that the NCC-MCC composite actually exhibits a flatter response, suggesting that it is even better than the standard when it comes to audiometric performance.
So let's revisit our objectives and see how we shaped up. Our primary objective was to achieve at least a 7.3% increase in specific modulus as compared to just pure cellulose paper. We found, on average, an increase of 12.3%, which would correspond to a cost savings of about 8.6%, thus exceeding this primary objective. Our secondary objective was to make a process that could be easily integrated into industry. We found that NCC and MCC were easily adopted into the cellulose matrix and are in fact even easier to create than currently existing paper composite materials that use Kevlar and carbon fiber. In these materials, you have to interweave the composite into the cellulose matrix. So not only is our product applicable everywhere that paper composites are used for speakers, but is in fact applicable everywhere any paper speaker is currently used. This includes low-end devices like in-ear earbuds that generally don't bother with Kevlar. Our tertiary objective was to take 2 cones of the same mass but different stiffnesses and see if our composite could increase the audio fidelity by at least 10%. Now, you could see by inspection, with the graphs that Zan just went over, that there was in fact an increase in audio fidelity. Now, however, due to technical limitations, we were unable to quantify that number, so it is left uncertain as to whether we hit that mark. Nonetheless, I think we have something very interesting here. Not only have we demonstrated a novel material that has a specific application in existing technologies, but we have made sure that it is simple, practical, and cost-effective. This could be implemented in industry today. So what's next for our project? First of all, we would want to quantify those frequency response results. This is not a difficult thing to do. We just need access to the proper software. Next, we'd like to optimize our composite formula. As we've mentioned, 1% NCC, 5% MCC were just values selected from within an acceptable range based on literature review. Next, we'd like to play around with these numbers and see if we can drive our efficiency even higher. After that, we'd like to partner up with industry. Then we'd be able to have help in building our speakers, which would allow for more uniformity across them and more precision in our measurements. With this, we would be able to tweak our formula more, as again, we'd have more control. Then we could create two cones of different masses, but the same stiffness. Then you could implement them into drivers with different size magnets and directly evaluate our cost-saving model. I'd like to extend a very sincere thank you to the people who helped make this project possible. First of all, to the University of McMaster's Sentinel Bioactive Paper Network for the donation of raw softwood pulp, as well as for training us in the paper manufacturing process. To the University of Waterloo's Audiometric Research Group for their help in our audiometric analysis. To Dr. Michael Tam for his expertise and consultation. And to Celluforce for the donation of nanocrystalline cellulose. Thank you very much for your time, and at this point, we'd like to field any questions you might have.
It's a nice talk. So open to question. You didn't justify why you have 7%. Can you elaborate more?
Why our primary objective was 7%? Well, again, that value was taken because we wanted a kind of round figure in terms of cost savings, because I would describe this initial step as more of a proof of concept. We want to show that it could be done. So 7.3%, we worked backwards. We said how much it would cost, or rather, how much of an improvement in specific modulus we need for that cost. And the idea with specific modulus is here. You can see that we found that within this regime, based on literature review, the mass of the magnet will inversely scale linearly with the specific modulus. So that's how we got that 7.3%.
So you assume in your model that you can translate that 150 gigapascal into the composite?
That's correct.
Literature review suggested that as long as we go up to 20% additives into the cellulose matrix, that we would be able to get a linear relationship in its...
Can you go to slide 16?
Mm-hmm. Oh, sorry.
Yeah.
Here we go.
You're saying that the composite is better than the standard.
Yeah.
Yes. By looking at this graphic, or did you do some differences in the signal?
Mm-hmm.
It is the lack of computational power to exactly evaluate how much the difference is.
You could subtract
That-
both curves, couldn't you?
Well, we actually don't have the Excel plot for this. We use this again with the audio research group. We are working with Dr. John Vanderkoy, who is head of that group, although he's currently in England, and he had somebody else man the software, but they aren't as equipped with it, so they didn't know how to export the data.
Third question.
Yeah.
Why don't you benchmark this against a real speaker? Because I can argue that your manufacturing process is so unsophisticated because you're doing this in a laboratory that doesn't matter what you add there, it's not going to make much a difference.
Well, that's a very good point. But the fact of the matter is, we did look into this, and speaker manufacturing, the paper that they'll do there, a lot of that is industry secret, and a lot of that is beyond the scope of our capabilities. We wanted to do a controlled experiment to see whether this material in particular would have good effects. And again, it was very easy to implement into the matrix, and I imagine that speaker manufacturers do have their own additives. I don't see why this wouldn't be compatible with them.
Wouldn't you be able to get a normal speaker from the market that is use comparable paper material and do this test? What is this standard? Is it a speaker from the market, or is it a speaker that you made?
The standard is the speaker that we made. We have compared it against the actual driver prior to having the cone removed. I showed that before and after picture. We still have speakers that have not been modified, same part, model number, same sized, every magnet and all that. And what we actually found is that our NCC MCC composite outperformed the standard, the industrial standard. Our composite was better in that case. The reason we don't compare it here is because we can't control exactly what's inside of that formula of the speaker that the industry uses. They use a variety of different types of resins and things like that, in addition to the cellulose to make their paper. So by being able to control the exact composition of the cone. That's what our standard is. We would like to just prove that the additives do have an impact on the audiometric results.
An example of such a resin would be a hydrophobic coating that is typical, especially for paper cones.
Okay. I have one question. Very quick. Can you go to slide page 5? So I just curious, it's very interesting for the cost. So where did you get this cost?
Okay.
Interesting.
Currently, the cost, nanocrystalline cellulose, up until very recently, as in the past 2 years, has been made only in laboratories on the kilogram scale. Recently, Cellulose, our sponsor, as of 2 summers ago, opened up a factory in Quebec capable of producing a metric ton of the product a day. Currently, the material is still very much a boutique chemical, as Kevin mentioned, with costs of $7,000 per kilogram. According to industrial representatives, as well as people in academia, the projected future cost, once the material is made, will be close to $25 to $50 per kilogram. Now, when we evaluated the cost of the speaker and the influence that this material would have on the cost of the new driver, we factored in using the $7,000 per kilogram cost. So we did not fudge the numbers. Only for the presentation did we show the projected future cost. But in all calculations, we used the $7,000 per kilogram value and still found that cost savings.
Good, thank you. Okay, I think stop here. Okay, so let's thank the business. Okay.